following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so far we've learned about partial derivatives and how to use them to find minima and maxima of functions of two variables or several variables. And now we're going to try to study more in detail how functions of several variables behave, how to compute their variations, how to estimate their variation in arbitrary directions. And so for that we're going to need some more tools actually to study these things. So more tools to study functions. And so today's topic is going to be differentials. And just to motivate that, let me remind you about one trick that you probably know from single variable calculus, namely implicit differentiation. So let's say that you have a function y equals f of x, then you would sometimes write dy equals f prime of x times dx, and then maybe you would, excuse me, can you please take a seat and sit down? That would be better. Thank you. So so we use implicit differentiation to actually relate infinitesimal changes in y with infinitesimal changes in x. And one thing we can do with that, for example, is actually figure out the rate of change dy by dx, but also the reciprocal dx by dy. And so, for example, let's say that we have y equals inverse sine of x. Then we can write x equals sine of y. And from there, we can actually find out what is the derivative of this function, if we didn't know the answer already, by writing dx equals cosine y dy. And so that tells us that dy over dx is going to be 1 over cosine y. And now cosine, the relation to sine, is basically 1 over square root of 1 minus x squared. And that's how you find the formula for the derivative of the inverse sine function. Okay? Formula that probably you already knew, but that's one way to derive it. So now we are going to use also these kinds of notations, dx, dy, and so on, but use them for functions of several variables. And of course, we'll have to learn what are the rules of manipulation and what we can do with them. So the actual name of that is the total differential as opposed to the partial derivatives, because, well, it's going to be the total differential because it includes all of the various causes that can change, all of the contributions that can cause the value of your function f to change. So, namely, let's say that you have a function f, maybe of 3 variables x, y, z, then you will write df equals f sub x dx plus f sub y dy plus f sub z dz. Okay, or maybe just to remind you of the other notation, partial f partial x dx plus partial f partial y dy plus partial f over partial z dz. Now, what is this object? What are the things on either side of this equality? Well, they're called differentials, and they're not numbers, they're not vectors, they're not matrices, they're a different kind of object. So these things have their own rules of manipulations, and we have to learn what we can do with them. So how do we think about them? So first of all, how do we not think about them? Okay, so here's an important pitfall to avoid. So important. Df is not the same thing as delta f. Okay, so that thing is meant to be a number. It's going to be a number once you have a small variation of x, a small variation of y, a small variation of z. These are numbers. Delta x, delta y, delta z are actual numbers, and this becomes a number. This guy actually is not a number. You cannot give it a particular value. All you can do with a differential is express it in terms of other differentials. So in fact, this dx, dy, and dz, well, they're mostly symbols out there, but if you want to think about them, they're the differentials of x, y, and z. So in fact, you can think of these differentials as placeholders where you will put other things. So of course, they represent, there's this idea of changes in x, y, z, and f. But so one way that one could explain it, I don't really like that, is to say they represent infinitesimal changes. Another way to say it, and I think that's probably closer to the truth, is that these things are somehow placeholders to put values and get a tangent approximation. So, for example, if I do replace these symbols by delta x, delta y, and delta z numbers, then I will actually get a numerical quantity, and that will be an approximation formula for delta f. It will be the linear approximation, or the tangent plane approximation. So what we can do, well, so let me start first with maybe something even before that. So the first thing that it does is it can encode how changes in x, y, z affect the value of f. I would say that's the most general answer to what is this formula, what are these differentials. It's a relation between x, y, z, and f. And in particular, so this is a placeholder for small variations.